Solid conductor. A solid conductor with the radius A is placed at the center of an outer conducting tube with an inner radius B and outer radius C. So on this cross section here, let's show what we have. Here's our inside conductor, and then this little rim here, kind of filling it in, is going to be the outer conducting tube. They both carry equal and opposite currents I. The current is evenly distributed over the cross-sectional area of each conductor. Derive an expression of the magnetic field for the following regions. That's part A. R is less than A, R is greater than A but less than B, and R greater than C. On the diagram below, sketch the graph of the magnetic field as a distance r from the center of the conductor. Include key intercepts. If the current in the outer tube is reversed, how would it change the answers to A1, A2, and A3? We're going to use Ampere's law, so first we'll construct an Amperian loop, which will be a circle of radius r, where r is less than A. So that's going to be a circle inside this inner conductor here, and that should be a dashed line, but you get the idea, I hope. The current enclosed for r less than A is the surface charge density here of this loop times pi r squared. The current through the entire central conductor will be the same expression except it has a radius A. Now sigma is the same, of course, wherever you are within the loop. We said it's uniformly distributed. So what we find now, the sigma and the pi cancel out, that I enclosed by this Amperian loop is I r squared over A squared. We use Ampere's law right here, and on the left side the magnetic field is going to be parallel to the ds vector everywhere. So when we do the integral, b dot ds becomes b ds, and when you integrate ds over the entire circle, you just get 2 pi r. So that's this term. Here's our enclosed current that we solve for up here, and we find the magnetic field inside the central conductor is mu 0 I r over 2 pi a squared, a linear function. Derive an expression of the magnetic field for the following region, A less than R less than B. This time our Amperian loop will be between the two conductors. Let's see if I can kind of sketch that in. That's horrible, but I hope you get the idea. It's between A and B. Here's Ampere. This time the enclosed current is just I. And again, we do the integral, the line integral here. We get b2 pi r. So our magnetic field is mu 0 I over 2 pi r. Find the magnetic field outside both conductors. So this time our Amperian loop, I can actually put the dashed lines here. It's outside of everybody, has a radius r. Now, what are the currents? Well, the currents enclosed are in opposite directions. So we'll arbitrarily assign one a positive I and the other negative I. Doesn't matter which one, because you add them together, you get 0. So we have Ampere's law. B dot ds is equal to mu 0 I enclosed, the line integral. Line integral, as always, reduces to b 2 pi r. It equals 0. Magnetic field outside this combination is 0. Sketch the graph of the magnetic field as a function of distance r. Let's do the easy part first. All the way up to point B, all we're worrying about is the inner conductor. We know that within the conductor it has a linear increase until it gets to the radius of the conductor, which is A, so it increases to a maximum value of mu 0 I over 2 pi a. Then it falls off as 1 over r until it gets to point B, and then you just substitute B in for r, and you get this intercept, mu 0 I over 2 pi b. And of course, outside, it's 0. Here's the interesting part. Well, we know the inner conducting magnetic field is decreasing as 1 over r. Okay? Now, what's being provided by this outer conductor where the current's in the opposite direction? It has an opposite magnetic field, and it's increasing as it's enclosing more charge. So let's call this guy positive, okay? So as the positive is falling off as 1 over r, we have the negative increasing as a factor of r. So that's going to make this guy decrease a lot quicker than 1 over r, so that's why the slope of that curve is larger than this curve. If the current in the outer tube is reversed, how would it change the answers to A1, 2, and 3? Well, the easy part is there's no change for A1 and A2 since the magnetic field only depends on the enclosed current. So when we draw the Amperian loop there and there, it has nothing to do with this outer conductor. Now, let's go out here where R is greater than C, and we have Ampere again. And the only difference now, certainly not this side, that'll be the same, we'll get B2 pi R, but we're now enclosing two currents in the same direction, so we add them this time, and they don't cancel out, so the magnetic field outside this combination is mu0 I over pi R.